So welcome again to the discussion of quantum dynamics. So as I said in the last session, we will discuss the harmonic oscillator problem in Schrodinger picture. Okay, so as you are aware that the harmonic oscillator is one of the simple physical system in which its potential is described as, for one dimension harmonic oscillator, the potential is described as V of x. I can write as half k x square, where k is called the force constant. Okay, and it is possible that we can write the same equation in another form as half m omega square x square. Okay, so we have defined a new term omega and m, and we can identify the m is mass and omega is angular frequency. So the k can be written as m omega square. So the V of x, the potential energy of a system, if you are writing this particular form of m omega square x square. So remember, this half m and omega square are just a constant for the system, and x is the variable. So if the potential varies quadratically with the position, then the system is called a harmonic oscillator. And we have many classical examples for the harmonic oscillator, like the spring mass system, So if you displace the mass from its equilibrium position, it will just oscillate above that equilibrium position. Okay, with some constant frequency and constant amplitude, if the displacement is very small. So that is an example for harmonic oscillator in classical physics. Another example is simple pendulum. So if you have a ball hanged on a string, then if you are kept in this orientation, this will be stable equilibrium, it will not oscillate anyhow. But if you displace it slightly from this position and release it, then it will start oscillating. So this will oscillate with again with some constant angular amplitude and constant frequency if the displacement is very small. Displacement theta is very small, and here again the displacement is x. Okay, so that is the classical example for similar harmonic oscillators, and we are very well aware about what are the possible positions. So the position x of t, I can write as some a cos omega t plus 1. Okay, so x is the variable which harmonically varies with the time, and a is the maximum value for the x, because the cos value, the maximum value for the cos can be 1. So the maximum value of the x can reach a. And the a is called the amplitude, omega becomes angular frequency, and phi is the initial phase, and then this phi and a we can find from the initial conditions. So that is what about x, and we can find the velocity x dot. The x dot is minus a omega sine omega t plus phi. That is, if we differentiate x with respect to time, we will get the velocity. And what about the acceleration? So the acceleration makes the root of t. You will get again a minus sign, not minus sign, you will get again an omega. So it will become omega square and sine become cos. So this will be minus omega square a cos omega t plus phi, and that will be minus omega square x of t. Okay. So that is what is called the acceleration. So these are simple systems in classical physics, and we know the energy of the system. The total energy is always half m omega square a square, where a is called the amplitude and this will be constant. And a can take any value. The amplitude may change depending upon how far you are oscillating the system, how far you are displacing the system. So that a is a continuous variable, so the energy can be continuous variable in classical terms. A and E are continuous, so we can have the continuous value for the energy for a simple harmonic oscillation in classical mechanics. Okay. Now we are going to look at what would be the harmonic oscillator problem in quantum domain. And there are mainly two different ways to solve this problem. So one of this is called the Schrodinger picture, and we will refer the Schrodinger picture for it. Okay, so you remember in Schrodinger picture, or as well as in the complete quantum mechanics, the state of the system is represented by a wave vector. Okay, so I will be using the wave vector here to represent the state of the system. So state of the harmonic oscillator represented as state psi, and obviously this will be a function of in Schrodinger picture. So we can take a representation for this problem. So the representation I am going to take is a position representation. So in position basis, the state I can write as in the correct side of t, and this we can represent simply as psi of x comma t, and it is called the wave function. So the wave function in position basis, there are two different bases we use usually, position basis and momentum basis. So in position basis, if you want to find position basis, take the inner product of psi of t with the position, it will give the psi of x. Okay. Next is how to find the time evolution for psi of x. The time evolution for psi of x is represented using the time dependent Schrodinger equation. And is given by IH cross dou psi of x t by dou t is equal to h psi of x t. And what is h here? H is Hamilton. Okay. So in general, h takes the form, the Hamiltonian is p square by 2m. It has two parts, the kinetic energy part and potential energy part. So p square by 2m plus v of x, and the v of x we already know for harmonic oscillator, which is half m omega square x square. So this become p square by 2m plus half m omega square x square. Now remember, we are using the position basis representation. In position basis, the momentum operator p is written as minus IH cross dou by dou x, and x is simply written as x. Okay, so hence my Hamiltonian can be written as minus, so p square will become minus square minus, so minus h bar square by 2m dou square by x square plus half m omega square x square. Then what would be our Schrodinger equation? So Schrodinger equation will take the form IH cross dou psi of x t by dou t equals minus h bar square by 2m dou square psi of x t by dou x square plus half m omega square x square. Okay, so we have to solve this differential equation, and by solving this differential equation we can get the possible energy of the system, and even if you can find the position of the harmonic oscillator and velocity of the harmonic oscillator, etc. Okay, so before that, now this problem, it seems to be a time dependent problem, but actually the Schrodinger equation problem, the harmonic oscillator problem is not actually completely time dependent, because the potential is time independent. So the time evolution would be very simple here. Okay, so in order to find that, what you can do is you can change the equation, the Schrodinger equation you can convert into a time independent Schrodinger equation. Okay, so there are a few steps we are required to solve it, how to move from a time dependent Schrodinger equation to a time independent Schrodinger equation. So for that, the first thing is we have to define the eigenfunction of Hamilton. So the eigenfunction of Hamilton, the eigenfunction of any operator or the operator which does not change by the action of the operator. Okay, so I will denote the eigenfunction of the Hamiltonian as un of x. So the Hamiltonian acting on un of x will give un of x, And you know that the Hamiltonian is something but the complete, the total energy. So the eigenvalue of the Hamiltonian will be the energy, and I will denote the corresponding eigenvalue as E. Okay, so these are eigenvalue equations. Okay, so the Hamiltonian is an operator acting on the un of x, gives un of x with the corresponding eigenvalue En. So En is the eigenvalue corresponding to un of x. The En is the eigenvalue of Hamiltonian corresponding to un. So this n subscript is very important here. Okay, so this subscript shows that there can be many eigenfunctions for a particular Hamiltonian corresponding to different eigenvalues. So for example, for n equal to 1, you have u1 and e1, and for e2 you have u2, for e3 you have u3. So for corresponding to different eigenvalues, you have different eigenfunctions. Okay, so this is just a eigenvalue equation. Okay, now remember this Hamiltonian is a Hermitian operator. It's p square by 2m plus v of x is a Hermitian operator. So Hamiltonian is a Hermitian operator here. So we already know the result that the eigenfunctions of the Hermitian operator, the complete set of eigenfunctions of Hermitian operator can act as a basis. So un of x can act as a basis. So since un of x can act as a basis, I can expand any vector, any function in that Hilbert space in terms of un of x. So we have a function psi of xt. So psi of xt can be expanded in terms of un of x. Okay, so that we will see in the next. Okay, so we have considered un of x as the eigenfunctions of Hamiltonian, and un of x can be treated as a basis because this is the complete eigenfunctions, the complete set of eigenfunctions for the Hamiltonian. And as we know in the mathematical formulation, the complete set of eigenfunctions of a Hamiltonian or a Hermitian operator can be taken as a basis. So we can expand any wave function in terms of this basis wave function. So I can expand my psi of xt in terms of un of x, then sum over n un of x. Okay, but there should be a time dependent part here. The time dependent part, the time evolution, I am giving to the expansion coefficient Cn of t. Okay, so therefore the wave function at time 0, you can write sum over n Cn of 0 and un of x. I can actually find what is the expression for Cn of t. For that, I require to know what is the time evolution equation for psi of xt. And that we have seen in this one, the picture, the psi of xt, I can write e raised to minus I by h cross ht into psi of xz. Okay, so if we add this e raised to minus I by h cross ht on psi of x0, what will you get? The psi of x0 is something but sum over n Cn of 0 un of x. So un of x is the eigenfunctions of the Hamiltonian operator. So when e raised to minus I by h cross ht acting on un of x, will get a phase factor times un of x. Okay, so that you can do it yourself. You will just do the steps for it. So I am writing the result. So sum over n, there will not be any change for Cn of 0. And when this act on here, you can be raised to minus I by h cross ht acting on un of x. And next step, this will become sum over n Cn of 0 e raised to minus I by h cross e and d un of x. So this step you can do it as follows. Okay, so it's a very simple step. What you can do is you can just expand this e raised to minus I by h cross ht in a series form. You know what is the series of any exponential function. So if you just expand it, you will get a very easy answer or easy step how to reach from here to here. Okay. So that you can do it as normal. I will give you this question as an assignment question to you. You can solve your answer there. Okay. Now, what is the advantage here? So from this step, we found an explicit expression for Cn of t. That means my Cn of t is nothing but Cn of 0 e raised to minus I by h cross e and t. Okay. So then hence my psi of xt I can write sum over n Cn of 0 e raised to minus I by x cross Ent Un of x. So this is a time evolution for any wave function. So if you expand, if you write the wave function in terms of the energy eigenfunctions, then the time evolution comes through this phase factor. Okay. Now we can apply, we can substitute this form of psi of xt in our time dependence on the equation. So what is my time dependence on the equation? I h cross dot psi of xt by dot t equal minus h bar square by 12 dot square psi by dot x square is a function of xt plus half m omega square x square into x. So if you substitute it here, we'll get very long equation, because if you look at the right side, there is a time dependent quantity here, so we have to differentiate the exponential factor, and there is a space dependent quantity here. So on the right side, I have to differentiate 2 times. Okay, so I am giving some steps. So if you substitute this, what you will get? So the right side, so left side become I s cross. If you differentiate this with respect to time, then this Cn of 0 and Un of x are constants. So if you differentiate this exponential term, you will get minus I by h cross En outside. So this becomes sum over n Cn of 0 minus I by h cross En e raised to minus I by h cross Ent times Un of x. So that will be your left hand side. And what about right hand side? It will be minus h bar square by 12. And I have to differentiate this with respect to x 2 times dot square Un by dot x square. But as far as x is concerned, the first 2 terms are constant. So I have to differentiate only Un of x. So the equation becomes sum over n Cn of 0 e raised to minus I by h cross Ent dou square Un by x square plus, and the last term is very simple, half m omega square x square sum over n Cn of 0 e raised to minus I by h cross Ent Un of x. Now recall again, Un of x is the eigenbasis, the eigenfunctions of the Hamiltonian operator. So therefore Un of x should possess orthogonality. That is, the eigenfunction corresponding to different eigenvalues should be orthogonal. It is Un of x, unit product Un of x and Um of x is always 0 if n not equals n. So this inner product is always 0. So that it shows that the Un of x are orthogonal, they are completely independent to each other for corresponding different eigenvalues. So therefore, while summing it over, this equation should be valid independently for each indices. For n equal to 1, this equation must be valid. For n equal to 2, this equation must be valid. Okay, so what I am saying is, if you expand this summation, there will be a series. For n equal to 1, you will get a 1 term, plus n equal to 2, plus n equal to 3, and on right hand side also you will get a term for n equal to 1, a term for n equal to 2. But this, but u1, u2, u3 are independent, and hence the left hand side and right hand side must be equal for each corresponding indices. Okay, so this equation must be valid for each corresponding indices. So therefore, I can remove the summation symbol and I can write this equation for a particular n. Okay, so since Un of x are orthogonal for a particular index n, I can write my equation as IH cross Cn of 0 minus I by h cross En e raised to minus I by h cross Ent the un of x equal minus h bar square by 2m Cn of 0 e raised to minus I by h cross Ent dou square un bar dou x square plus then the last term half m omega square x square Cn of 0 e raised to minus I by h square Ent. Okay. So this must be the condition, and for this condition must be valid for every n. The reason is all n's are all un of x are completely independent to each other. Okay, so then here you can simplify this equation because many terms would cancel from both sides because Cn of 0 is common everywhere. So Cn of 0 will cancel, and this exponential phase factor will also cancel. So what are the remaining things? Okay, and the left hand side also you can make this h cross would cancel here, I into minus I would cancel. Okay, so I will write this right hand side first. Okay, if you write this right hand side first, I will get minus h bar square by 2m dou square un by dou x square plus half m omega square x square un of x equals En un of x. So what we have got now? So we have got a new equation. This equation is corresponding to un, which is only function of x, there is no time here. Now this equation is called time independent Schrodinger equation. Okay, so time independent Schrodinger equation are the differential equation obeyed by the energy eigenfunctions. And this is nothing but, if you look at this equation, this left hand side is nothing but h into un. So what we have here is, and we already know this, we already stated, is h acting on un of x is En un of x. So this equation, this eigenvalue equation for the Hamiltonian is nothing but the time independent Schrodinger equation. Okay, so once you know what is un of x, then the psi of xt is very simple because psi of xt, the time evolution you can find from this equation. Okay, so for the time being we are not interested in the time evolution. So first what we will find is the energy eigenfunctions. Once you find energy eigenfunctions, we can find what is the corresponding energy eigenvalues. What are the possible energies for harmonic oscillator? Okay, so this equation is called time independent Schrodinger equation. Okay, so we can just summarize what we have learned till now. We have started with the potential energy of harmonic oscillator, and from this first we have set up the time dependent Schrodinger equation. Now in order to find a time independent Schrodinger equation, what we have defined is we have defined the energy eigenfunctions of this problem. So energy eigenfunction denoted by symbol un of x, which are the eigenfunctions of Hamiltonian corresponding to the energy eigenvalue En. Okay, so then our next aim is to find the differential form of the time independent Schrodinger equation. So for that, what I have done is first we have expanded the wave function in basis un of x, and I have found the explicit time dependent form of psi of xt, and the entire time evolution I have given to the expansion coefficient not to un of x. Un of x is the basis, which is the energy eigenvalue, and which is completely independent on time. Okay, and I have found the form of Cn of t from the time evolution equation of psi of xt, and I have got my psi of xt of this nature, this Cn of 0 raised to minus I by h cross Cn b un of x. Okay, so from this I have substituted the explicit form of psi of xt in the time dependent Schrodinger equation. From that I have arrived a new equation which is called the time independent Schrodinger equation. Okay, so our next task is to solve this time independent Schrodinger equation. Now the solving of time independent Schrodinger equation is not very straightforward. The first thing is I have to read how to change the variable of this problem. Okay, so first we'll change the variable, and after changing the variable we'll find a new differential equation and we'll solve that differential equation. Not very straightforward. First we'll go for an asymptotic solution, then we'll go for a series solution, then we'll find what are the problems in it. Okay, and then finally we'll arrive by finding what are the possible energy eigenfunctions and the possible energy eigenvalue. Okay, so next we can have a task of solving time independent Schrodinger.